Google DeepMind has just released a massive update to AlphaFold, including a new web app that makes high-fidelity protein structures freely available to the public. This is the breakthrough many have been waiting for, but there is a critical misunderstanding about what this actually means for robotics. While we have finally solved the problem of predicting the blueprint, we have not solved the problem of building the machine that can execute it. By the end of this video, you will understand why the next bottleneck for roboticists is not computational power, but the fundamental mechanical inability of current actuators to handle the flexible, dynamic shapes that AI can now design. For years, the field of structural biology was stuck in a dark age where predicting how a protein folds was nearly impossible. We knew the sequence of amino acids, but we had no idea what the final three-dimensional shape would look like. That changed when AlphaFold demonstrated that deep learning could predict these structures with near-experimental accuracy. Now, with AlphaFold 3, the system goes further. It does not just look at proteins in isolation. It models how proteins interact with DNA, RNA, and small molecule ligands. The new inference pipeline allows for the generation of complex, multi-component assemblies that mimic real biological machinery. The web interface makes this accessible without needing to run complex Docker containers on your own hardware. This is a triumph of digital prediction. We can now generate a perfect digital twin of a biological machine in seconds. Here is the thing that most news coverage misses. Just because we can see the blueprint does not mean we can build the house. The gap between the digital model and physical reality is where the real engineering challenge now lies. When AlphaFold 3 predicts a structure, it often describes a molecule that is highly flexible, dynamic, and constantly shifting. It might show a protein chain that bends, twists, and interacts with a ligand in a way that changes the overall shape in real time. This is not a rigid block. It is a soft, breathing entity that relies on the specific material properties of the amino acids to maintain its form. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Current robotic systems are built on a completely different paradigm. Industrial robots, and even most advanced soft robots, rely on rigid linkages, hydraulic cylinders, or pneumatic actuators that are designed for repetition and precision in a fixed environment. They are excellent at moving a heavy object from point A to point B. They are terrible at mimicking the subtle, continuous deformation of a biological complex. When you try to use a standard robotic end-effector to manipulate a structure that AlphaFold 3 has designed, you run into a fundamental failure mode. The predicted shape collapses under its own weight or the forces of the actuator because the robot is trying to impose a rigid control strategy on a soft, compliant target. This creates a new problem that we call the stiffness mismatch. The digital model assumes a specific material stiffness and flexibility that allows the structure to hold its shape through molecular forces. The robot, however, applies external forces that are orders of magnitude larger and less nuanced. If you try to grab a predicted protein complex with a rigid gripper, you are essentially trying to hold a jellyfish with a steel vise. You will crush the target or fail to grasp it at all. The control systems we have today are designed for position control. They assume that if the robot moves to coordinate XYZ, the object will stay there. But biological shapes do not stay there. They flow. They adapt. They require a control architecture that can manage continuous deformation, not just discrete positions. The AlphaFold 3 repository highlights this limitation by focusing entirely on the accuracy of the prediction. It gives us the coordinates, the sequence length, and the interaction maps. But it does not give us the inverse design tools needed to translate those atomic coordinates into a feasible mechanical linkage. There is no module in the current system that says, to build this structure, you need a material with this specific Young's modulus and this specific actuation frequency. The roboticist is left to bridge that gap manually. You have to take a perfect digital simulation and then spend months or years designing a physical system that can approximate it, often sacrificing the very flexibility that makes the biological shape useful. Consider the interaction problem. AlphaFold 3 excels at showing how a ligand binds to a protein, inducing a shape change that triggers a biological response. In a simulation, this looks like a smooth transition. In a physical robot, replicating this requires an actuator that can change its shape in response to a chemical signal or a control loop that can sense that tiny deformation and adjust the grip instantly. Current sensors and control loops are simply not fast or sensitive enough to handle the degrees of freedom in these protein DNA ligand complexes. We are trying to control a system with infinite degrees of freedom using a controller designed for a system with 6 degrees of freedom. This shift from the folding problem to the interaction problem means that the bottleneck has moved. It is no longer about calculating the structure. It is about the mechanical actuation of multi-component assemblies. The new challenge is designing compliant, sensor-rich control architectures that can manage the continuous deformation of the target shapes without crushing them. We need to move away from position-controlled rigid robotics towards systems that can adapt their stiffness and shape in real time. Until we develop actuators that can match the bandwidth and dexterity of the biological shapes we are designing, AlphaFold 3 will remain a powerful tool for simulation, but a limited tool for physical manufacturing. The immediate utility for industrial robotics is currently theoretical because the tools for physical execution do not yet exist at the same scale as the tools for digital prediction. The requirement to request model parameters and the limitations on the public server further complicate the timeline for adoption. We are in a transition period where the digital world is running ahead of the physical world. The future of biomanufacturing will not be defined by how fast we can predict a structure, but by how quickly we can invent the mechanical systems capable of building it. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.